All right, ladies and gentlemen, we are talking about intermolecular forces and their effects in liquids and solids. This is chapter 11 of the Brown Book, chapter 10 of OpenStax. And here we go. So, in this illustration, we are showing you the different structures in the three states of matter, the structures of the particles. And so, in the structure of a solid, you have particles that basically have vibrational motion only, right? They have no translational motion. They're not moving around from place to place. When you add heat to them, when you add kinetic energy to them, they can turn into a liquid where you break apart those the crystal structure of the solid, and then they start to move around a little bit. Okay, and so liquids move around a little bit, and then you add more kinetic energy to them, and they're able to break free of those intermolecular forces and get into the gas phase where they are freely moving. The particles are bouncing off the walls of the container, and they are in free motion. So let's talk about the difference between intramolecular forces and intermolecular forces. Intramolecular forces are very strong bonds. They are the forces of bonds, the forces that hold the H to the Cl, right? The sharing of electrons there that causes that hydrogen atom to be bonded to the chlorine atom. But intermolecular forces are these weak forces between molecules in a sample. So if you have the hydrogen part here is positively charged, the chlorine part is negatively charged, and so there's an attraction there, right? Like a little magnet. Okay, so that's what intermolecular forces are. These are causing the forces that deal with physical changes and physical properties, whereas the intramolecular forces are causing properties like the chemical properties of a substance. If we look at those in more detail, the intermolecular forces, the forces between the molecules, are the explanation for the different boiling points, melting points of substances, their vapor pressure, their viscosity, their adhesion and cohesion. And we'll talk about all of those properties specifically. Intramolecular forces we've kind of talked about, right? Because we've talked about the stability of molecules, the bond strength of molecules, how they react together, which is all related to the bonds, right? The bonds can be polar or nonpolar within a molecule, or they can be ionic or covalent, right? Within a molecule or within a substance. So intermolecular forces hold the atoms together. They are collectively referred to as van der Waals forces. And these van der Waals forces come in two varieties. You have the London-Dispersion force and the dipole-dipole attraction. Now, there is a particularly strong dipole-dipole attraction between OH and H and HF molecules that have those bonds. And we'll talk about those specifically, but they are not different. They are dipole-dipole attractions, right? They're just particularly strong dipole-dipole attractions. So what causes this? Well, the London dispersion force is caused by moving electrons. So because electrons are moving constantly, right, in a very small period of time, we're talking like femtoseconds, right? Really small amounts of seconds, right? These electrons might be at one point in time on one half of the atom more than the other half, right? And so this would impart an attraction to the nucleus of the neighboring atom, right? And so the electrons are attracted to this nucleus. This electron's attracted to this nucleus, right? This electron's attracted to this nucleus. And you could get a temporary polarity within that atom, right? Towards the other atom. So you have kind of a partial magnet being formed, but it's very instantaneous. It happens very quickly. And so because it happens very quickly, it goes back to not happening very quickly as well. And so London dispersion force is a very small force, right? But collectively, if you have enough of them, right, they can cause interesting, cool things to happen within a molecule, between molecules. Okay, this London dispersion force is named after a German-born American physicist, Fritz London, and this explains a lot more about it. So just so you know, the London dispersion force named after a dude, not after a place. So here's our evidence. Everything that we know in chemistry, we have to base upon observations, right? Here's our observations that help to confirm our idea about London dispersion forces. So you have methane down here with very few electrons, right? He has 10 electrons, right? Carbon has 6 and hydrogen has 1, and there's 4 hydrogens. So 10 electrons down here, we would expect him to have the lowest boiling point, right? Because he has the least amount of energy required to break those bonds, right? To break those attractions between molecules. As you go to silane, which is silicon with hydrogens all around it, then you have a higher boiling point because it has more electrons. The more electrons you have, the more chance those electrons could be maybe unevenly distributed, right, at one point in time. And so that would cause an attraction force. And you see that with silane. Also with the next down the periodic table to germanium, down the periodic table to tin, right? These guys, this has the most electrons, so it would have the highest boiling point, right? It's also related to molecular weight or molar mass, but that's just because the number of electrons is also related to molar mass. So it's not because of the molar mass, it's because of the electrons. A very important distinction when you're talking about London dispersion forces. It's linked directly to number of electrons, right? And kind of indirectly to molar mass. It's also linked to the surface area of the molecule. So if you have, these are all pentane, right? Let's see if I can move this. Can I move this? Can't move this. There we go. We have neopentane, which is pentane like in a ball, right? And then you have isopentane, which is pentane that's branched. And then you have normal pentane, which is pentane that's not branched, right? All linear. When it's linear like this, it has the most opportunities for intermolecular attractions because there's more surface area to come in contact with other surface areas. Now, they're not actually coming in contact with each other, but the forces are, right? So the forces between these molecules have much more ability to interact when there's more surface area, right? So the higher the surface area, the higher the intermolecular forces, the more electrons, the more intermolecular forces. So those are two different things. Geckos. Oh gosh, geckos are so cool. And the reason why geckos are so cool is because they can stick to surfaces because of London dispersion forces. This is how this works. So geckos have toes, right? So their hands are branched into toes, right? Each of those toes has setae on the end of the toes, right? So the toes are branched, right? And then they have branches on the toes. And then those setae are branched even further and have spatulae on the end of them. So branched and then branched again, right? So you have a hand branched to a foot, branched to a toe, branched to setae, branched to spatulae, right? And so there's gazillions of these spatulae, right? And what happens is when a gecko puts his foot on a surface, right, those spatulae actually interact atomically with the surface. And there's attractions between the atoms of the spatulae and the atoms of the surface that causes the gecko to be able to stick to them. This is amazing, right? Because a gecko can use one toe and stick to a ceiling, right, and just hang there, totally stable, right? Because London dispersion forces of attraction are attracting those spatulae to the atoms of the surface that it's adhering to. Crazy, absolutely crazy. I could talk about gecko's feet for days, but I'm going to stop now because we're going to talk about dipole-dipole attractions. Now, dipole-dipole attractions are stronger than London dispersion forces because dipole-dipole attractions are caused by permanent dipoles. So if you're looking at the water molecule here, the oxygen part of the water molecule, which is right here, right, has a negative, is more electronegative than the oxygen. So it gets the electrons more, which causes a partial negative charge on the oxygen. There's a partial positive charge on the hydrogen because the hydrogen is less electronegative. And so the oxygen gets the electrons more, right? Hydrogen gets the electrons less. So hydrogen has a positive charge, partial positive charge. The oxygen has a partial negative charge, right? That is able to interact with the positive charge of neighboring water molecules. So the oxygen's negative charge interacts with the positive charge of a neighboring hydrogen, right? And they line up like this so that all of the oxygens are oriented towards the hydrogens all the hydrogens oriented towards the oxygens. And the reason why this is such a strong dipole-dipole attraction for OH, NH, and HF bonds is because the O and the H are so small, right? They're super small atoms. And so they're able to interact very closely. If you look at the measurements here, the total measurements of distance between the oxygen of one water molecule and the neighboring oxygen of another water molecule is 2.8 angstroms. Angstroms are 10 to the minus 10th meters. So these are like atom-sized distances, right? So there are atoms that are bigger than 2.8 angstroms. There's tons of atoms that are bigger than 2.8 angstroms. So they're actually like kind of forming like a molecule, right? Because if you have the bond, the intramolecular force within the hydrogen and oxygen between the water molecule, that bond is only 1 angstrom, right? The attraction, the distance between the particles that are attracted to each other, is 1.8 angstroms. So it's only a little more than twice as far away, a little less than twice as far. And so that means that it's very, very close, very strong attraction. And water will arrange itself into this crystal structure when it freezes, and this is a snowflake under electron micrograph. So cool. So cool. So permanent dipoles from these bonds, from an OH bond, an NH bond, and an HF bond, are particularly strong. Now, the ones we're going to care about most are the OH and the NH, because OH, and then you can be bonded to something else, NH, and you can be bonded to something else, but HF is just it. That's it. That's the molecule, right? You can't have HF bonds to something else, right? So HF itself is particularly interesting, right? Because hydrofluoric acid is not a strong acid, right? It does not dissociate completely when you put it in water. The reason why is because the HF bonds between molecules, right? The HF and then another HF, and they're bonded to each other, are very, 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 very strong. Much stronger than if it released the H and the F on its own, and those were surrounded by water molecules, right? So HF itself is a very interesting molecule in this way, right? Because it's a weak acid. It doesn't dissociate when you put it in water, but it does react. It's very reactive, right? Because it's got just small ball of charge, right? So the evidence to support our super strong dipoles of hydrogen bonding is in this graph. So if this were a linear relationship, right, and this was like a relationship between bond polarity, right, the least polar bonds down here, the most polar bonds over here, or something like that. Like if you're talking about the most electrons, right, these guys have the most electrons, these guys have the least electrons. So why, with the least electrons, are these guys such high boiling points compared to their neighbors? Well, that's because of hydrogen bonding. The hydrogen bonding is what keeps these guys together in a sample and gives them a very high boiling point relative to their size. This can apply to, or this does apply to, our explanation of why DNA forms the structure that it does. So DNA forms an alpha helix because the two branches, the two sugar phosphate backbones, are connected by their bases. Their base pairs that connect together are thymine and adenine because they have two hydrogen bonds. They form two hydrogen bonds, very stable. And guanine and cytosine form three hydrogen bonds, very stable, right? Very stable. And so adenine will not bond to guanine because it would be 2 on 3, right? Thymine doesn't bond to cytosine because it would be 2 on 3. So the only way that they can bond like this is between thymine and adenine and guanine and cytosine. And this forms very strong attractions between the base pairs, right? And you have DNA. All right, so here's some review questions. These review questions basically get to the heart of, do you understand the idea of London-Dispersion Forces, dipole-dipole attractions, particularly strong dipole-dipole attractions that are called hydrogen bonds? I'm not going to go over these in the screencast, but you should have a class discussion. So if you want to pause the video, have a class discussion, feel free. and we'll move on. So liquids. Liquids have the properties that they have because of these intermolecular forces, the forces that bind the liquids together, the molecules in the liquid, right? And so viscosity is the first one. Viscosity is the property of a fluid's resistance to flow. So something that is very highly viscous has very strong intermolecular attractions. So if you think about molasses, right? Molasses is a very concentrated sugar solution, and you have very strong attractive forces between those sugar molecules and each other in the liquid, causing it to flow very slowly, right? This is also important for motor oil, right? And the viscosity rating on your motor oil just describes how thick it is, right? So 5W30 or 10W40, something like that, right? Then you have surface tension. Surface tension is a cohesive intermolecular attraction that causes the liquid to minimize the surface area. So it means that they stick together, right? Caused by cohesive forces. So the molecules want to stick to each other, right? And when they stick to each other, it causes the molecule to have lots of surface tension. So it's hard to break that surface tension. Intermolecular forces that bind a substance to its surface are called adhesive forces. So that causes them to stick to things, right? And so this combination of adhesive and cohesive forces will cause liquids to rise up through very narrow tubes called capillary tubes, and this is called capillary action. And so let's look at this. So if you look at the surface tension idea here, right, the molecules are attracted to each other, right, on the surface, and then the cohesion is the molecules being just attracted to each other, right? Capillary action, illustrated here, where you put a paper towel in a bowl of wine, right? The bowl of the wine will crawl up the paper. And the reason why is a combination of adhesive and cohesive forces. So if you look at that, the adhesive forces will want to bind the solution to the walls of the container, right? And then they will be pulled up the container by their cohesive forces. So they're sticking together, they're holding hands, and the one end is grabbing. So it's grabbing, holding, right? And then they lift each other up, right? This is water has very strong capillary action, right? But then if you look at mercury, mercury being a metal, right, does not have those um, adhesive forces, right? Mercury does not want to bind to the sides of the tube, right? So it will be repelled by the tube, and it will just kind of stay with itself, right? It likes to stick to itself. Phase changes are another phenomenon that can be explained by intermolecular forces. So as you are changing something from a solid to a liquid, and you're adding heat to that, the amount of heat that you are adding in order to complete that process of taking it from a solid to a liquid to melt a substance is called the heat of fusion. Okay. Um, and that amount of heat is the amount of heat that is required to break the crystal structure, right? To break the bonds of the crystal structure, or the attractive forces of the crystal structure, more accurately, right? And then if you take that liquid and you add more heat to it, you can vaporize it, right? And that amount of heat that you have added to take it a liquid to a gas is called the heat of vaporization. Now, the heat of vaporization is always going to be much greater in value than the heat of fusion. The reason why is because the heat of fusion, you are only breaking that crystal structure, the attractive forces of the crystal structure, and you are allowing those molecules then to flow, but they're still attracted to each other, right? They still have all the other intermolecular forces. In order to break all of those other intermolecular forces, then you have to boil it, right? And that is the heat of vaporization. So for most substances, the heat of vaporization is much, much larger than the heat of fusion. Okay. There's also a phenomenon called sublimation when a solid goes directly to a gas. This generally happens at low pressure, right? And there's a heat associated with that, right? Because you do have to add heat to a solid to break its bonds and get it straight to the gas phase. You have to break all the bonds, right? Um, and so that is the process of sublimation. You've probably seen sublimation before if you've ever filled an ice cube tray, left it in your freezer for the winter. and then come back in the springtime and say, where's my ice? I don't know what happened to the ice. Your ice disappeared. It didn't really actually disappear. It just vaporized, right? It went straight from a solid to a gas. It's sublimed. Okay, vapor pressure is inversely related to intermolecular forces. So the stronger the intermolecular forces, the lower the vapor pressure, right? The weaker the intermolecular forces, the higher the vapor pressure, because then if you have weak intermolecular forces, it is much easier for you as a molecule to break free and get into the gas phase, right? And so diethyl ether over here will have a higher vapor pressure under normal temperature than ethyl alcohol will, right? Because diethyl ether, it has polar bonds, right? It has dipole-dipole attractions. But ethyl alcohol has hydrogen bonding abilities, right? And water has even more hydrogen bonding abilities. So it's going to be even stronger of attractive forces, and so lower vapor pressure. And so let's review these ideas. Okay, so if you look at surface tension and viscosity values for these substances, diethyl ether, acetone, ethanol, and ethylene glycol, right? And you're going to try to explain their differences in terms of size and shape of the molecules. So if you look at diethyl ether versus acetone, both of them have uh, dipole-dipole attractions, right? The oxygen here in the diethyl ether is electronegative, much more electronegative than the carbon, right? So it's going to make a polar bond in between these guys here, right? But acetone has the oxygen on the end, right? So the oxygen on the end is more accessible, right? It's more accessible to interact with other things. So its surface tension is going to be higher, and its viscosity is going to be higher because it has a higher attractive force for itself, right? But then you look at ethanol. Ethanol has a hydrogen bonding ability, right? And ethylene glycol has two, because it has two hydroxides on the end of it, right? So it has two spots for hydrogen bonding, whereas ethanol only has one. So this ethylene glycol would have a much higher attraction for other ethylene glycol molecules than ethanol would have for itself, for other ethanol molecules, right? And so the surface tension is increased between ethanol and ethylene glycol, and the viscosity is increased as well, right? And so this makes sense, right? So now I want you to try it. Here's a different substance. This is water, right? And we're looking at the surface tension and the viscosity at different temperatures. So what effect do you think temperature would have on the surface tension, the ability of the molecule to stick to itself, and the viscosity, its resistance to flow? Okay, so think about that. Talk amongst yourselves. Come up with an idea. I look forward to hearing it. So now, structures in solids are also related to the ideas of intermolecular forces, right? But solids tend to have structures that are the structures of solids are related to the shape of the solids, kind of a little more so than the attractive forces. The attractive forces cause the shape, though, so it's kind of six one, half dozen the other. But here's the different types of shapes. You could have an amorphous solid. Amorphous solids do not have any order to them. They don't have a crystal structure, right? They're just there in solid. Crystalline solids, though, are ordered. They have a crystal packing structure. This repeating structure is called a unit cell. And so if you want to look at the type of unit cell that it has, it's related to the lattice points. So if you draw it as a cube, right, and you look at where are the centers of these atoms in this cube that I've drawn in the structure, then you can have a primitive cube, a body-centered cube, or a face-centered cube. And this is what it looks like. A primitive cube, when you draw your box, right, there's nothing in the middle, okay? And you just have on the outsides. So it looks like this, right? And you have divided the centers by the edges, so you've divided them into eighths, right? And so then at the end, you have one atom right here, right? A body-centered cubic is when you draw this structure, you are able to put an atom in the center of it. And so it's body-centered, right? There's an atom in the center of this structure. And then you have 8 atoms on the corners, right? Face-centered cubic, when you draw your cube around the crystal structure, you will see that there are atoms in the faces of your cube, right, that are sliced in half. Okay, so that gives you this face-centered cubic model. Okay, the packing scheme, you can have more than just those, right? You can also have hexagonal close packing. So there's 6 atoms in there in that center, and those can be arranged in a different way. The packing efficiency is related to how much space there is in between the particles. So the less space, the higher the packing efficiency. Things that have very high packing efficiency are very dense, right? And so they'll have properties associated with that density. Depending upon what the atoms are that make up that packing structure, depends upon the other properties, right, that it has. And so in solids, you can have molecular solids. Molecular solids are held together by the London-Dispersion forces and the dipole-dipole attractions, right? They're intermolecular forces that are keeping them together. When you have a covalent network solid, though, it's different. They are actually held together by covalent bonds. And so I'll talk to you about the specific examples of that. Okay, these molecules are super hard. They are super strong. And so you are able to make a covalent molecule into a very strong molecule, or very strong solid by the making sure they're all bonded together, like everything's bonded together. Ionic solids, we're familiar with these, right? They consist of cations and anions. They're held together by the opposite charges that cations and anions have, right? And so they're very stable in that way. And then you have metallic solids. And we're going to talk about the metallic solid sea of electrons model. Okay, and I'll tell you what that means. So when you have ions in an ionic compound, that causes it to be hard and brittle, right? Because they are very strongly attracted to each other. And the only way you can get them apart is like physical separation, right? You smash them with a hammer, boom, they will shatter, right? If you hit them hard enough. And so that's a result of those electrostatic attractions. Now, when you have a metallic solid, it's different. So, a metallic solid, we have our sea of electrons model. And our sea of electrons model holds up pretty well, even though it doesn't make all the sense in the world. Here's how it works. I'm going to explain it to you. So if you have an atom, a metallic solid, like let's say gold, right? Your metallic solid is consisting of, we think of it as those metal centers, so the nuclei of the gold atoms, right? They are sitting next to each other in a space, right? And in between them, all around them, is a sea of electrons. The sea of electrons is flowing like water flows, right? It's able to move around and it's shared between those metal centers, right? This allows us to explain how metals can be malleable, how they can be hammered, because those sea of electrons is very squishy, right? Because it's a sea. You can hammer metals. It also allows those metals to conduct electricity, right? Because the sea of electrons is moving, right? And so you can pass electric current through it, which is moving electrons, right? And those moving electrons can move with other electrons, and life is good, right? So that's the model that works really well to explain a lot of the properties of metals. Then you have a covalent network. A covalent network is completely bonded together. So like diamond. If you think about diamond, diamond is actually carbon atoms in um, hexagons, but the hexagons are all bonded to other hexagons, right? And so you have this crystal structure that's very, very strong because it's made up entirely of bonds. There's no intermolecular forces, there's only bonds, right? That's what makes diamond so hard. If you look at the different crystal structures of carbon, diamond is the covalent network example, but the amorphous solid example is coal. It's the same atom, right? It's just carbon. But if they're not bonded together in a covalent network, like coal isn't, then it's just a mush. Then it's just a lump, right? And it's very easy to break it apart. You can throw it into a furnace and burn it. I mean, you could burn diamonds too, but like that would be a bad idea, right? This is also the same covalent network that is used in glass, right? That's why silicon dioxide, so sand, is heated up and made into a crystal, and that's glass, right? And so glass is a network like that they're all bonded together, right, in that covalent network. It's pretty cool. And then if you have a molecular solid, then you've got a lot of variety depending upon the various intermolecular forces that are at play, right? And so that's it. That's all I got for you. So you should be good to go. Let me know if you have any questions. All right. Have yourself a great day.